Now we'll prove 22.15.3. This formula will replace the right-hand side of the first formula 22.15.2 by an integral. To prove this, we take the difference between this guy and this guy. The trick is that we're going to split this difference into two parts. By adding and subtracting a sum, which can be seen as an approximation to this integral. And now you see there are two parts. Our next goal is to show that both of these parts are big O of x log of x. This is what we are going to prove next. For the first part, we are going to use the first formula in theorem 421, Abel's summation, namely the equation 22.5.1, with C1 equal to 0, Cn equal to an minus the integral from n minus 1 to n of log of t dt times 2. And f of n equal to the absolute value of r of x over n. And now let's look at left-hand side and right-hand side of this formula, 22.5.1. The left-hand side will become simply by plugging in the definition for c sub i's and f of n's into this sum. And the right-hand side will become and now let's figure out what c of x is. C of x, by definition, is a summation of c sub n for n less than or equal to x. Because c1 is 0, this is summation from equal to 2 to the floor of x. And now let's plug in the definition. Here we have merged all of this integral into one integral, namely from 1 to floor of x. You can see the correspondence. But this integral is computable. There is an antiderivative t times log of t minus t. So we use the Newton-Leibniz formula. Now, what happens if you try to remove the bracket from this part? After removing the bracket, I claim it becomes minus 2x log of x plus big O of x. Do you think you can verify this by yourself? You can pause this video and try to work it on your own, but I will give the answer anyway. To verify this, we simply take the subtraction x times log of x minus x floor times log of x floor. We can first majorize this guy by monotonicity to floor of x plus 1 times log of floor of x plus 1. And now we can compute this. As x goes to infinity, you can see that these two parts together is little o of x. If you divide both sides by x, you see this part divided by x will go to 0. This part alone will go to 0 as x goes to infinity, and this part is bounded by 1 after dividing by x. So they together will be a little of x. But this part here is a big O of x. So they together is minus 2x log of x plus big O of x. So we verified this part. Now, what is the summation of an for n less than or equal to x? What about this part? Do you remember? By definition of a sub n, together with the Selberg's asymptotic formula 22.14.3, the summation is 2x log of x plus big O of x. So now let's plug this guy back to the last line of this equation. What do we get? Now this term here is 2x log of x plus big O of x by Selberg asymptotic formula 22.14.3. Now we can cancel this 2x log of x with 2x log of x. So they together will be a big O of x. Now we plug c of x equal to big O of x back to the right hand side. The c of n will become big O of n. For the sum, we take everything into big O notation. However, the function in the parentheses of big O must be a non-negative function. So we are not supposed to use a parenthesis, but absolute value here. Namely, the sum is equal to big O of this sum as a function of x. And second part is a big O of x. For those who cannot see this immediately, let me remind you the definition for R. Because percent of x is big O of x, so R of x is also a big O of x. Here I'm talking about theorem 114. So, because x divided by floor of x as x goes to infinity is a bounded number, so R of x is bounded. Therefore, this product is still a big O of x. However, at this point, we don't know how to deal with this part. This part looks complicated, and for the moment, we don't know how to simplify it. What I do is I'm gonna leave a question mark here. We'll address this later because the similar issue will appear again for the second part. So far, we are working on the first part. To summarize, we have proved that first part, which is equal to the left-hand side of our summation under these assumptions is equal to the right-hand side of our summation, which we just simplified as this complicated term plus big O of x. Later we'll prove the thing with a question mark is equal to big O of x times log of x. So the first part is big O of x times log of x. But now let's leave this alone and look at the other part. Let us simplify this part. The simplification for this part is relatively straightforward. First, let's put the absolute value outside of the whole thing. And we split this integral so that it aligns with the upper limit of the sum. Namely, we do a truncation at the floor of x. This is the truncation I meant. And now we use a triangular inequality to throw this guy outside of the absolute value sign. And for the first part, look at this integral. We're going to break this integral into a sum so that it aligns with this sum here. And next, we're going to merge these two sums of integrals and apply the absolute value inequality for integrals. This guy is less than or equal to the summation for n bigger or equal to 2 less than or equal to x, and integral from n minus 1 to n of this absolute value. So that is the first part. We'll leave this alone and look at the second part. What about this? This guy can easily be bounded because the upper limit minus the lower limit for this integral is bounded by 1. Log of t is less than or equal to log of x. And r of x divided by t, by definition, this is psi of x divided by t minus x divided by t. And this is a big O of x divided by t by theorem 414. Because psi of x is big O of x. So this absolute value for t between floor of x to x is a bounded number. So big O of 1 for t between floor of x and x. So this integral in total will be bounded by 2 times the difference of the limits is bounded by 1 times this guy is a big O of 1 for t between these two limits, and log of t is bounded by log of x. And together is a big O of log of x. So again, as in our treatment of the first part, we are left with a complicated term involving r. And I will leave a question mark here. As before, we want to show this guy is equal to big O of x times log of x. Now, to understand these two complicated terms better, we shall study for t bigger than t prime equal to 0, the relation between the absolute value of RT and the absolute value of RT prime. By triangle inequality, we know their difference is bounded by RT minus RT prime absolute value. Now we plug the definition for R back to here. It is psi of t minus t, and same for the t prime part. Now, by triangle inequality, this is bounded by our assumption t is always bigger than t prime, so this part is always positive. And by the monotonicity of psi, this part is also non-negative. So we have, by dropping the absolute value sign, if you regroup these four terms, we get this. Therefore, if we define this sum, psi of t plus t, as a function f of t. Remember, psi of t minus t is r of t, and f of t is defined as psi of t plus t. It turns out this difference is bounded by f of t minus f of t prime. And this difference, the first observation is that it must be a big O of t, because f is a big O of t, which follows from the fact that the psi of t is big O of t by theorem 414, which we have used many times. Now, in view of this thing, we will study the following sum involving f. The summation for n less than or equal to x minus 1 of n times f of x divided by n minus f of x divided by n plus 1. On one hand, by monotonicity of f, this is always bigger or equal to 0. Here, x is always a positive number, and actually we always assume it is bigger or equal to 2. And now, let us give this an upper bound. So, each individual summand is non-negative, so the sum must be non-negative. And now let's give an upper bound for this. To do this, we'll try to create a telescoping sum in here. And we split this. Because the first part is telescoping, most of the terms will be cancelled out except for the first and the last. The first term, namely when n is equal to 1, is simply f of x. And the last term, namely when n is the floor of x minus 1, this is floor of x times f of x divided by floor of x. And we can merge this term and this term together, because here n starts from 1. But that is f of x divided by 2. If we merge these two together, what do we get? We get sum from n equal to 1 less than or equal to x of f of x divided by n. So this term comes from this part together with this part. And now we're going to simply throw away this non-negative term. This is always non-negative. So whole thing will be bounded by just the first term. But by theorem 414, this is what? The summation for n less than or equal to x of big O of x divided by n. And now you move this summation into the parentheses. It will become big O for n less than or equal to x of x divided by n. And this guy, by Euler theorem, if you pull out this x, what is the summation of 1 over n for n less than or equal to x? By Euler theorem, namely the theorem 422, this is big O of x times log of x. So we have an estimate of this as big O of x log of x. And that is precisely what we need. Now we move back to the first part, the first question mark. Now this guy, remember this absolute value from our derivation above is bounded by the sum in terms of f. Actually here, I don't need to use the less than or equal sign because big O already means upper bound. So I can safely use just the equal sign. And by what we just proved, the sum is big O of x times log of x. And this is precisely what we need. So we have addressed this part. Now what about this part? For the second part, we essentially do the same. First, we'll replace r by f. And then we look at the integrand. By monotonicity, because t is from n minus 1 to n, this integrand is bounded above by, now we replace this t here by the smallest one, namely n minus 1, and replace t here by the largest one. It follows that this integration becomes vacuous, so we can remove the integral. And also observe by the monotonicity for f, we can also drop this absolute value sign. And now, because log of n is always less than or equal to n minus 1 for n bigger or equal to 2. You can prove this by calculus. And therefore, we obtain another sum where this estimate applies perfectly. You simply replace n here by n minus 1. In this setting, you will see And this guy is again a big O of x times log of x. And this verifies the second part. So we have proved that both this and this are of order big O of x times log of x. But the together is precisely this difference. And this finishes the proof of 22.15.3.